Welcome to Spring LIB.
This is the answer to Chapter 30, problem number 32 from the Smith Organic Chemistry textbook. And this problem asks us to draw a mechanism for this cyclization reaction between farnesyl diphosphate and isopentenyl diphosphate. And then it asks us to comment on some unusual features of this reaction. So to start, I've drawn farnesyl diphosphate here. So the first thing that's going to happen, and remember, we've seen this before in other problems in this chapter. So the diphosphate group in farnesyl diphosphate is willing to leave. So the electrons will go to the oxygen and will form a carbocation. Right. So after the diphosphate leaves, we're here where we have that carbocation. And so at that point, that's when the isopentenyl diphosphate is going to come in and react. So here is our isopentenyl diphosphate. And the electrons in this double bond will attack the carbocation that we formed in the first step. And so that will give us this intermediate. So give me a moment to draw it out. Oh, and actually I just noticed that I made a mistake in the previous intermediate. So this double bond should not be here. It should instead be here. So I apologize for that. And so back to drawing this intermediate. So here is the product of this addition. Let me just particularly note that nitrogen there. And of course, we have a carbocation here now. And so it's important to note that nitrogen there because that's the nitrogen that a base in solution, and we're just going to represent base with capital B there. So a base is going to come and grab that proton, grab that hydrogen, and the electrons will revert to that bond to make it a double bond. And so the product here is now this. So basically, all that we've done is if you look at our starting farnesyl diphosphate, we've basically just extended it by 1 unit, right? So it looks like we just tacked on another repeating subunit, another one of these, and in effect, that's what's happened so far. So what we need to do now is redraw this in such a way that it's easy to visualize the cyclization that's going to occur here. So in order to do that, we can start at one end here. Just bear with me. This may take me a moment to draw. Oops. Okay. And then here's our OPP, our diphosphate. Okay, so obviously the point of redrawing it like this, oops, and I dropped a methyl group. There we go. Okay, so the point of redrawing it like this is just because it makes it much easier to show this cyclization that's going to occur. So once again, the OPP group is very willing to leave, so we can just show that bond breaking, the electrons going to that oxygen there. And so what will happen next is that, you know what, I'm not even going to redraw this entire thing. So here's what I'll do. So there's one terminus, and then the other terminus is going to look like this now. Oops. And so we'll do this, and we can use this sort of squiggle curvy line connecting these just to show that there's a whole ring going on over here. And that cuts down on time, having to redraw the ring, making mistakes in drawing the ring, and then, right, so nothing from this portion of the molecule here has changed at all and is really affected by the rest of this reaction at all. So we might as well just leave it out. And I will redraw it for the final product. But until then, there's not really any point. And so we now have a carbocation here. And very similarly to the first reaction in this mechanism, this double bond is going to attack this carbocation. And so the product of that is going to be this. And again, I'm going to draw this simplified version. That is ugly. Right. So actually now, of course, that closed the ring. So and again, we can just draw a squiggle there. And so we'll draw, I'm actually going to draw it this way, proton there, hydrogen there. And then, of course, we will have a carbocation here. And so what will happen now, again, exactly as happened in the first reaction in this sequence, is that a base here will show up, snag this hydrogen. These electrons will revert to there to reform the double bond. And unfortunately, it looks like I'm going to have to draw my product on a new page. So So there we go. There's the final product. Flexibean. Right. So the other part of this question that we're asked is, what is unusual about this cyclization reaction? And what's unusual about this cyclization reaction is this right here, what I'm going to show you in red. So a carbocation has formed here in the mechanism that I've drawn, and that's a secondary carbocation, whereas a carbocation could form elsewhere to make a tertiary carbocation. So if instead of that carbocation, we formed a carbocation right. So if instead of that one we formed the carbocation here, so the ring wouldn't close here; it would close here instead, and that would be a tertiary carbocation. And of course, tertiary carbocations are more stable, but it would result in a different ring too. It would result in a 14-membered ring instead of a 15-membered ring. So the reason for this, the reason that this is able to happen, is that in reality, the electrons here are sort of bouncing back and forth. So each of these positions has somewhat of a carbocation. The difference being when the carbocation is at this position, the position it's actually in, it allows us to close this ring down and make this ring, which for whatever reason is preferential. And so that's what's unusual, is that we would expect this to form as a tertiary carbocation, or at least to rearrange to a tertiary carbocation, but that's not what we see. And of course, the result, as I said, is this molecule, Flexibean. And so that's the answer to chapter 30, problem number 32.